Hello and welcome everyone to our presentation about the virtual validation of autonomous driving functions in urban areas with mixed traffic. We are very happy to get the opportunity to present our topic within the Stuttgarter Symposium 2021. I am Caroline Handel and I work for TWT Science and Innovation. Within this presentation, Lutz Morich from AUDI and I will give you an overview of the research project SAVe. I will focus on the photorealistic modeling, the scenario generation and the driving simulation, which were the main topics of TWT's contribution within the project. Before we jump into the presentation, let me give you a short introduction to the company TWT. The name stands for Technisch-Wissenschaftlicher Transfer, which means that we transfer scientific results into industry. We have a broad portfolio ranging from engineering, systems engineering, over communication and change management to enterprise data solutions. Recently, in the winter semester 2020-21, TWT even started a cooperation with the University of Stuttgart. Together with the Research Institute of Automotive Engineering and Vehicle Engines Stuttgart, we held a lecture Automated Shuttle Vehicle in the course Autonomous Systems. There, we provide our simulation tool Tronis for exercises. And this tool will be introduced later in this presentation. And now, I will happily hand over to my co-referent.
I would also like to welcome you to our presentation. My name is Lutz Morich. I work for AUDI in Ingolstadt. I had the honor to lead the SAVe project. Today, after a brief presentation of the project content, I will give you an in-depth look in the simulation of traffic in the overall model, and, at the end, an outlook to future activities.
Das Projekt SAVe ist richtig wichtig, damit Ingolstadt auch in Zukunft ein bedeutender Fahrzeugentwicklungsstandort bleibt.
SAVe ist wichtig, um gemeinsam die Mobilität der Zukunft planen zu können und die Region ein bisschen lebenswerter zu machen.
SAVe ist wichtig, um reproduzierbar kritische Verkehrssituationen zur Absicherung automatisierter Fahrfunktionen zu erzeugen.
SAVe ist wichtig, denn wir werden viele Funktionen des autonomen und automatisierten Fahrens nur auf die Straße bringen, wenn sie vorher getestet und abgesichert worden sind. Und dafür hat das Projekt SAVe wichtige Grundlagen konzeptioneller und praktischer Natur gelegt.
As the prominent previous speakers have already indicated, the SAVe research project deals with a methodology for a testing site in which automated and connected driving functions are developed and approved. The name SAVe is the acronym for Functional and Road Safety in Automated and Connected Driving. But this only works in German. The motivation for building up such a methodology comes from the fact that we will not be able to approve the automated driving functions of level 3 and higher adequately by physical testing methods. Maybe you have heard of those distances to be driven for one approval that would be in the range of billions of kilometers. To avoid this, the tests have to be automated and parallelized, and therefore virtualized. So we chose Ingolstadt as the subject of investigation for such a virtual test site. Why Ingolstadt? One important reason is the fact that the percentage of highly equipped cars with back-end connection in the traffic is very high there. By this, we have a perfect starting point for calibrating our traffic simulation. The project with our partners from industry, science and municipality started in May 2018 and was finished by the end of last year. The €6 million project was funded with €4 million by the Ministry of Transport and Digital Infrastructure. Besides the technical tasks to build a basis for vehicle and infrastructure development by simulating and analyzing driving scenarios and traffic, we also examined social issues. By using the simulation model, we could inform the citizens about the technology and also do research in needs and opportunities of human beings in terms of autonomous and connected driving.
As you could see, the project consisted of 10 extremely different partners. Coordinating a research collaboration of 10 independent players from industry and academia is not always easy. Additionally, ensuring that research activities are connected, synergetic, synchronized, and target-orientated seems utopian. But there is a way for this to happen almost by itself. This is how we did it. We looked for an intersection in Ingolstadt, which became the object of investigation for a wide variety of applications and questions. Criteria for the selection were traffic density and accident frequency. As you can see, we have found one, the so-called Hindenburg-Ringler intersection. We installed a traffic observation camera on the roof of a building directly next to the crossroads. Here are some examples of the applications we have developed.
Starting on the upper left side, you see how we are able to analyze the traffic-specific trajectories and as well detect scenarios involving all road users with the help of the traffic observation camera. Underneath, it is shown that we simulated driving as well as the movement of VIUs. The video shows an interactive study we made with test persons using the simulation. At the bottom, you can see how to derive critical scenarios from the simulation that are used, for example, to investigate the effectiveness of car-to-X communication in driving tests. The picture at the bottom right shows how we applied the developed semi-automated virtual environment setup process to build up the environment model. We have found a way to combine the two worlds of geoinformatic and driving simulation formats and tools. The first word talks CityGML and the second OpenDrive. At the right, you see weather conditions to be simulated for scenarios by using ray tracing methods. By coupling microscopic and submicroscopic simulation, almost arbitrary driving and traffic scenarios can be generated or resimulated using the real traffic as dynamic environmental input, which is shown at the upper right side. At the top, different applied infrastructure sensors for the improvement of traffic safety are investigated and optimized with respect to their effectiveness. By this way, a wide range of disciplines could work together simultaneously and very effectively to develop a variety of methods that can be applied in virtual test fields. After this short overview, Caroline will now go on into more detail on a few of these examples.
Results of the German Federal Statistical Office show that the greatest misconduct by drivers of passenger cars occurs when giving way or when turning. In this context, yielding and turning stands as the largest deterioration group. Thus, we wanted to create a virtual testing environment that would cover exactly those cases. Since we already established the real-world research intersection as the most critical point of urban traffic infrastructure, we decided to create a digital twin of it. For a high-detailed 3D environment, The Blender 3D modeling software was used to model various representations ranging from the architecture and illustration to construction and vegetation animations. The 3D modeling process produces a digital 3D object, known as a mesh, that can be loaded into external software. The first step was to manually model the intersection as displayed in the bottom right screenshot in high detail. The main focus was put on the visual and photorealistic aspects. Textures were realistically recreated, especially for the buildings and asphalt. A realistic virtual representation of environments offers a huge advantage for the training and testing of virtual sensors, since they can, for example, access near-accurate data in the case of a camera feed. In addition, visually more appealing simulation scenarios with reflections and realistic environments generate better acceptance among consumers of demonstrators, as well as in probationary studies. The resulting meshes can then be imported into several simulation tools. The video on the right-hand side and all following images show the intersection in Tronis, TWT's own simulation tool that enables real-time and physics-based simulations for subsequent driving applications. It offers an environment for virtual prototyping and validation of driver-assistance systems and robotics. Tronis itself is based on the Unreal Engine. This allows us to utilize the potential of 3D visualization and the physics engine it provides. Our tool provides several common sensor models such as camera, radar, or LiDAR that can be placed freely in the environment and on vehicles to observe the surroundings and to test the vehicle behavior in the virtual world accordingly. In the real world, it is very difficult to investigate potentially dangerous edge cases. But for testing sensors, you need high-quality samples. With the help of a photorealistic simulation, this data, such as the feed of a virtual camera, can be compared with a real camera output and thus can be directly used as a substitute data. Other possible use cases include the testing of LiDAR or radar sensors in neuronal networks. Tronis takes over the complete vehicle behavior and the control of the dynamic maneuvers. Through distance sensors, events are triggered for each vehicle, which execute braking, steering, speed adjustments, or lane changes. The maneuvers executed in Tronis also adapt to the Open Scenario XML standard. Furthermore, it features an automatic import of standardized map data to design photorealistic 3D environments and corresponding scenarios. For example, in addition to the conventional manual editing of a scenario, entire road networks can also be imported automatically via click. For our simulations, we explored the novel innovative technology ray tracing, which enables a realistic simulation of lighting effects. Ray tracing allows the rendering of indirect light reflected from corners, semi-transparent objects through which light shines, and realistic shadow effects in the simulation. The entire simulation scenario therefore looks much more realistic. With this technology, we created various weather scenarios. Sunny, rainy, snowy, and foggy weather conditions include rendering of surface textures and particle effects that can be dynamically adjusted. For realistic weather effects, high-resolution materials and complex particle effects are used. The particles represent snowflakes and/or raindrops and provide a resource-optimized solution to create realistic animated environments. The weather effect objects include a wide range of settings for the visual effects that control the actual function of the materials. In addition, different weather effects can be combined to create a wide range of effects such as heavy snowstorms or rainstorms. This is especially useful for creating these special corner cases that are difficult or even impossible to test deterministically in real-life environments. With the application of various weather effects, it is also important to simulate the surface texture that inevitably arises from the conditional weather circumstances. Examples are the highly reflective water puddles and the snow-covered asphalt, sidewalk and grass surfaces. Technologies have been developed to visually and simulatively model these surface conditions. In real time, the snow or rain surface effects can be dynamically turned on or off. To ensure safety in autonomous driving functions, extensive tests are required that cannot be covered by real-world driving tests alone. The complexity of a simulated scenario, in addition to the dynamic elements, is derived from the representation of static objects such as the road network, as well as vegetation, houses or signs and guardrails. The importer of TRONIS and the standard OpenDrive for the description of such static objects transfer those complex scenarios into the virtual world. The OpenDrive description format contains all static objects of a road network that allow realistic simulation of vehicles or other traffic participants driving on roads. In order to render the complete environment, additional description formats for static 3D roadside objects, such as trees and buildings, are needed. The dynamic content of driving simulations, such as vehicle maneuvers, is described with OpenScenario. These two standards complement each other and cover the static and dynamic content of the vehicle in the loop and formulate the complete scenario's description. The data of OpenDrive and OpenScenario is organized in a hierarchical structure and serialized in the XML format. These files can be verified and validated, edited as well as imported and exported by simulation tools. Furthermore, content editors can be designed on this standardized data format. The format is technology and vendor independent, standardized and continuously improved by ASAM. The TRONIS importers allow the XML format to be evaluated on the originated objects to be put into the world in an automated process. This involves a conversion between the two different data units. The 3D objects in the virtual environment receive a specific surface texture and a 3D model. Scenarios can thus be represented uniformly across tools using standardized map data.
In order to breathe life into the urban virtual test site, the traffic has to be mapped realistically. Essentially, besides the geometrical description of the roads and lanes, three main components are needed for this. First, statistical data. Second, traffic counts. Third, traffic light circuits. I will give you more details of these main components in the following slides. For essential source-destination relationships, thus who travels from where to where, a wide variety of sources are used. The attractiveness of districts, the reasons for traveling, and the residence to workplace relationships. We have the advantage in Ingolstadt that the largest employer has statistically recorded and evaluated working time models and residential location patterns. The second component is traffic counts of induction loops at traffic lights. The picture shows the places where counting takes place. With the counted values, one can calibrate the traffic model. Our project partner EFS has additionally developed an optimization procedure based on the count data via machine learning. Results are available via the link below. In the SAVe project, measurement data from the Audi vehicle fleet was also added to provide further information. This serves as a preparation in order to basically be able to process vehicle data that would principally be available in the future. For example, from the service function Ampel Info Online. The third pillar of the traffic model is the switching states of the traffic lights. From the outside, they seem quite simple, but in the details, traffic light circuits are quite complicated. This challenge is increased by the fact that the software of traffic lights is mostly based on different proprietary formats of the few manufacturers. The video on the left below shows the cyclic traffic light switching implemented at the intersection we looked at earlier. Once this information has been incorporated into the simulation model and the model has been calibrated, it looks like the video on this slide. Cars, heavy traffic, public transport buses, cyclists, etc. are represented as individual elements. This allows the depicted traffic to function as a dynamic environment for the urban virtual test site. How passengers or drivers experience this in the simulation is now explained by Caroline.
Another application of driving simulation is to enable users to experience and drive a single vehicle independently in a virtual complex road traffic environment. Users can take the wheel of any vehicle in a realistically modeled interior. A number of different input and control options are available to the user. It is possible to control the vehicle directly by simple keyboard inputs and to rotate the camera, corresponding to the virtual driver's head, by mouse movements. In addition, steering wheels and pedals can be used for virtual immersion to get a real vehicle control feeling. Virtual reality headsets can also be integrated and allow users to immerse themselves directly into the virtual world. In this context, studies with test volunteers have been conducted with the help of virtual reality in order to create acceptance towards autonomous driving. Along the path to autonomous driving, in addition to technical development, it is also crucial to bring people's acceptance along with it. Studies provide sophisticated insights into where people stand in relation to autonomous driving and how we can establish an appropriate expectation of the new technology in society. Volunteers directly experience a virtual autonomous driving in a 5 to 7 minute test scenario. Feedback was collected directly and realistic impressions were gathered. The virtual driving scenarios range from urban to rural areas and highway traffic conditions.
After we finished our SAVe project at the end of last year, the question naturally arises, what comes next? The sober inventory is that we have essentially created methods and tools for a virtual test field. We have understood the methodology, but our result is still only comparable to the small hand tool that we have mastered. Our goal, however, is a digital twin that can be operated as a whole, using Ingolstadt as an example. Compared to the hand tool, it is more like a complex production machine that we see here in this picture. We will implement all the ideas and the learnings in the follow-up project SAVe Now. We have significantly strengthened the cooperation and increased the project volume and, thankfully, are being funded again by the Ministry of Transport. This picture illustrates the project. We are going to build an extensive digital twin with which we want to answer complex questions of mobility, environmental protection, and traffic safety in urban areas. And we have already started 4 weeks ago. Thank you for listening to our presentation, and now Caroline and I would be happy to answer your questions.